Phase change materials, PCMs, are a class of substances that absorb or release significant amounts of latent heat during phase transitions, most commonly between solid and liquid phases, at specific temperatures. This unique thermal behavior allows PCMs to store and release large quantities of thermal energy, making them invaluable in applications requiring thermal regulation, energy storage, or controlled heating and cooling. The key feature that defines phase change materials is their ability to undergo reversible phase transitions with a substantial enthalpy change, typically without a major change in temperature during the transition. PCMs are generally classified into three broad categories based on their chemical composition: organic PCMs, inorganic PCMs, and eutectic mixtures. Organic PCMs include paraffin waxes and fatty acids, which offer good chemical stability and are non-corrosive, though they generally exhibit lower thermal conductivity. Inorganic PCMs such as salt hydrates and metallic alloys tend to have higher thermal conductivities and latent heat values, but may suffer from phase separation or supercooling. Eutectic PCMs are mixtures that melt and solidify at a single, well-defined temperature, combining advantages of both organic and inorganic materials. One of the most prominent applications of phase change materials is in thermal energy storage systems. In buildings, PCMs are integrated into walls, ceilings, or floors to passively regulate indoor temperatures by absorbing excess heat during the day and releasing it at night, reducing the need for active heating and cooling. In solar power plants, PCMs are used to store excess thermal energy collected during peak sunlight hours, allowing for continuous electricity generation even when the sun is not shining. Thermal management of electronics is another important field, where PCMs help dissipate excess heat in components like CPUs or power electronics, extending the lifespan and performance of devices. In the packaging and transportation industries, PCMs are used to maintain temperature-sensitive goods, such as pharmaceuticals and perishable food, within required temperature ranges during transit. Advanced PCMs tailored for cold chain logistics can maintain target temperatures for extended periods without external power sources. In textiles, PCMs are integrated into fabrics to create smart clothing that adapts to changing environmental temperatures, offering comfort in varying climates. Aerospace and automotive sectors also leverage PCMs to manage thermal loads in critical components under fluctuating operational conditions. Beyond these thermal applications, phase change materials have found remarkable roles in emerging technologies, especially in the field of data storage and electronics. One of the most significant scientific developments is the use of chalcogenide-based PCMs such as 2sp2te5, GST, in phase change random access memory, PCRM. These materials exhibit reversible transitions between amorphous and crystalline states with distinct electrical resistivities, enabling fast, non-volatile memory devices with high endurance and scalability. The rapid and localized heating induced by electrical pulses enables data to be written or erased, while the non-volatility of the states allows long-term data retention. In optical data storage technologies such as rewritable CDs, DVDs, and Blu-ray discs, similar chalcogenide PCMs are used to switch between reflective and non-reflective states, encoding binary data. The contrast in optical properties between the two phases allows for high-density storage and reliable read/write cycles. Research is also ongoing into the use of PCMs in neuromorphic computing, where the material's phase-switching properties are exploited to emulate synaptic behavior in artificial neural networks. Specific examples of PCMs include paraffin, a mixture of linear alkanes such as C18H38, which is widely used in building materials due to its melting point around 60 degrees Celsius and good thermal cycling stability. Salt hydrates like calcium chloride hexahydrate, CaCl2-6H2O, have higher energy densities and are often used in industrial heat storage systems. For electronic applications, chalcogenide compounds such as 2sp2te5 and agon-sp-Te are among the most studied due to their fast switching speeds and well-defined phase transitions. Metallic alloys like NSP or bean systems are also being investigated for high-temperature PCM applications in aerospace engineering. In summary, phase change materials are a versatile and vital class of functional materials with broad applications across thermal management, energy efficiency, electronics, data storage, and emerging computing paradigms. Their tunable phase transition properties and high latent heat capacities make them powerful tools for both conventional and frontier technologies, with ongoing research expanding their applicability in smart systems and sustainable energy solutions.